function of an expectation value of an operator. I don't know if you remember that. I do. And we basically did a calculation at the very end, kind of rushed because time was ticking away. And the result of that was somewhat remarkable. And I'm going to repeat some of that just to kind of like make you understand why that is so relevant. So let's first go back to our classical picture. All right, so let's say in all of these cases, think about an electron that is zipping about in space, and we'd like to find a description of this electron. Okay, we can do it classically or quantum mechanically. So if we do it classically, I could, try to figure out, for instance, the momentum of this electron. And in the classical case, what I have some sort of a function. Okay, let's say x of t, and from x of t I can determine the velocity as a function of time, because that's just the derivative of x of t with time. And from that I can determine the momentum of this electron. All right? So if the electron can be described classically, then I could have my momentum at any time. Okay, so what does that mean? That means if I put this electron in a box, okay, that dot is the electron, it's in a box, and I'm going to do a measurement. Basically, I'm going to peek into the box and see what is the momentum of this electron at a given time. All right, so let's say that there's nothing happening in the box. Let's say the electron is just zipping about, and it doesn't really change its velocity. Let's say the velocity is constant. Okay, then if I do a measurement, what I'll find is I measure a certain momentum, and the value of the momentum I will call P1. Okay, that's it. Just measure P1. And then a moment later, I'm going to do the same measurement. No, I just said the speed of the electron doesn't change, so that means I should find P1 again. Okay? This electron is just having its own speed, and every time you look at it, it says, oh, my momentum, by the way, is P1. Okay, so measurement 3, the same result, measurement 4, and so forth. So if I would basically make a plot or a histogram of the value of momentum for each of the measurements, then all the measurements will be P1, so I get one spike. Okay, I just get P1 because that is the value of momentum for this electron. That seems pretty trivial. But in quantum mechanics, we can have a very different scenario. Okay, so let's do the same analysis for the same electron, but now the electron is described quantum mechanically. Okay, so the same electron, but now in the quantum mechanical description. So what is now my descriptor? My descriptor now is the wave function. I don't know what it is, I don't know what it looks like, but I'm going to say that is my wave function, psi, which is a function of x and t. And now I would like to know the momentum. How do I get from the wave function to momentum? Well, last time we said we have to calculate basically the expectation value of the momentum operator. Okay, and that was this thing. That integral where the momentum operator is sandwiched between the wave function. On the left side, you see the complex conjugate of the wave function. I'm assuming that the wave function is normalized, which is a very reasonable assumption. And I can now find the momentum of this particle if I know the wave function, and I can calculate the expectation value in the following way. So what we did on the very last slide from Friday's lecture was that we said, well, the wave function has this general form. Okay? This general form. It was basically a linear sum of contributions that have a Cn in it, which is a weighing factor, times a function that is an eigenfunction of the momentum operator, which I call phi n. There's a whole bunch of n's, and if I sum over all the n's, I sum over all possible eigenfunctions of the momentum operator. So what I'm doing is, I say the wave function is essentially a linear sum of all the eigenfunctions of my momentum operator and each of these eigenfunctions has a certain weighting factor in front of it. If the weighting factor is very high, then this eigenfunction is a very good description of my actual wave function. If the weighting factor Cn is very low, then that particular phi n doesn't really contribute as much. So last time we basically did this, okay? We basically put the shape of this wave function into the expectation value expression. Okay? And we found something interesting. And what we found is something that corresponds to this situation. So, if I would do a measurement of this electron and I ask the electron, what is your momentum? Tell me, please. I would like to know. Then, the electron will say, my momentum is P1. Okay? But if I ask again, then suddenly it may say, it's P5. What does P5 mean? P5 is basically N, okay? So that means, basically it says, I am best described now, at this point, by the eigenfunction phi n equals 5. So I get P5, the momentum that corresponds to the electron if it were in eigenstate P5. If I do another one, could be P3 or anything else, any n. N is kind of a random number at this point. Okay? I could measure any possible momentum that corresponds to the momentum of the eigenfunctions of the operator. Okay? So what do I get in the end? I get something like this. I do a whole bunch of measurements. I get some of them happen a lot, like this guy, and some of them happen much fewer times. I get a distribution of values. Sometimes I measure one momentum, another time I measure another momentum. If I add them all up, I get a distribution of momentum that I can measure. A probability distribution. So, my expectation value is the weighted sum of all these momenta. Okay? You see, these are all the possible momenta that I can measure, and each one of them has a certain Cn squared. That is the probability. The probability that you measure this, or that. This is a probabilistic outcome. The outcome is not guaranteed. It's guaranteed to fall in this distribution, but it doesn't tell me where in the distribution my next measurement will lie. That's a probabilistic outcome. That's not a deterministic outcome. Because deterministic means I know for sure what the next measurement is going to be. That was the case in the classical example. It's not the case in my quantum mechanical example necessarily. Major difference. Okay. So let's look at this funny way of describing a wave function. We've done it now several times. Okay? We say a wave function can be described as a linear sum over the eigenfunctions of a given operator. On the previous slide, those eigenfunctions were the eigenfunctions of the momentum operator. But it could be of another operator too. So this is the most general description of my wave function. A linear sum over eigenfunctions of an operator. The Cn has something to do with the weighting, how much each of these eigenfunctions contributes to the total wave function. So what I can do is the following, just to get a little bit of a sense of what this description actually means. So if I take this wave function and I multiply it by phi I, what is that? That is one of the eigenfunctions from the complete set. I say, what happens if I multiply my wave function by one of these eigenfunctions? Okay, so we can calculate that. Okay? It looks like this. I just fill in the shape or the form of big psi, and I get this. So what I can do, I can move that function phi I, and I make it sit next to phi n. All right? And then I'm saying, okay, I'm going to integrate that result over x, over all x. What does that mean? It basically means this is the so-called overlap integral. It is the overlap of my function, my wave function, psi, with one of the eigenfunctions. And it's an overlap integral. An overlap integral is a very important concept in quantum mechanics, because it basically tells me, or asks me, what is the content of phi in psi? Think about, let's say, the Cartesian coordinate system. Let's say if I have a regular function, okay, a function in space, there's a function of x, y, and z. If I have that function and I multiply it with the x, basically the direction x, I'm asking what is the overlap of my function along the direction x? Basically, what is the projection of this function on x? I just make a projection onto the x-axis. This is the same thing. I make a projection of psi onto the phi axis. How much of phi is in this psi? That's what the overlap means. Okay, so I can calculate that. What I have to do, this integral sign is now going to be just over these functions, these eigenfunctions. Looks pretty scary, but in fact, it's not, because we have already seen the general outcome of that integral. Because these are eigenfunctions from a complete set, and it simply says the overlap integral is going to be 0 if I is not equal to n. And it's 1 when it's equal to n. Therefore, it has this solution, delta I n. The Kronecker delta says 1 if I equals n, 0 if I is not equal to n. So basically, if I say that n must be equal to I, otherwise it's 0, I only have one value left from the sum, that is Ci. The answer is Ci. Thus, the overlap of my general wave function with an eigenfunction phi is Ci. Ci is the projection. The value of the projection of my wave function along one of the eigenfunctions. That's how much the eigenfunction phi contributes to the total sum. Does that make sense? Some people say, Some people say, I'm not saying anything. Yes?
So Ci is in general like, is it like a constant value that determines like the percentage?
Yeah, you can think of it. I mean, it's not exactly the percentage, but it's basically, it's an amplitude, but it's related to the probability, which you can think of it as a percentage. So it's related to the percentage of phi that contributes to psi. Psi is a sum over all wave functions with certain fractions of each. And this one relates to the fraction of each. That's it. Okay. So this will come back to us several occasions, and we're looking at it over and over again to come to grips with this kind of stuff. And now I will just start looking at the wave function itself. The wave function itself is a funny thing. It's a descriptor of the electron. It's not something you can see directly, but if you operate on it with an operator, let's say the momentum operator or energy operator, you'll get information about momentum or energy, right? But there's something else that we can say about this wave function, about the physical meaning of this wave function. And that was provided by this handsome young man. He says, this is Max Born, by the way, he says that this expression, the modulus squared of the wave function, times dV. dV is basically a small volume element, okay? dV. Very tiny volume element. So, the wave function, the modulus squared of the wave function, times this really tiny volume, is the probability of finding the electron in that tiny volume. In other words, the modulus squared of the wave function is a so-called probability density. Okay. So what does that mean? That means this. If I take the modulus square of my wave function and I'm integrated over the entire volume that is relevant to my problem, space, entire space, if I integrate over all space, then I can say the following. If this wave function describes an electron, then the electron must be somewhere, and therefore the chance of finding it is going to be 100%, which is 1. Okay? For a normalized wave function, it should be 1. It must be a finite value in general, but for a normalized wave function, that must be 1. That 1 means now that the electron must be somewhere in space. If this wave function has a non-zero value, or non-zero, if it's a non-zero entity, then the integration of modulus square of the wave function over the entire space must be 1, which means the electron must be somewhere in space. This is good. It's good for us because it gives a little bit of a meaning to this wave function itself. It also helps us kind of like analyze kind of like several problems, okay? Because it gives some physical meaning to our wave function. So let's look at that. The definition of this modulus square is the wave function multiplied by its complex conjugate. What does that mean? That means that if the wave function happens to be complex, which means it has the imaginary number I in it, that the complex conjugate is that same function, but now the I becomes negative I. Okay? That's what it means. So that's the definition. So, if I'm now taking this most general form of the wave function, which is this pesky format, once again, okay, this linear sum over eigenfunctions of some sort of operator. And I multiply that by itself like this. And again, for each sum, I'm going to give it its own dummy label. N is not the same as M necessarily. Okay? It runs over the same distance, over the same numbers, but they don't run at the same pace, for instance. So basically, N and M I keep different for now, just for bookkeeping's sake. I can write it in this way. So basically, it's a double sum that sums over N, that sums over M, and I get Cn with a little asterisk times Cm. That is the outcome. Times the wave function, the eigenfunctions themselves. Okay, so I have the side, the phis, phi n star, phi m. I just multiply those two things between parentheses, and this is what I'm getting. So if I have to integrate that thing over space, I have to integrate what I just wrote down. The integration only goes over things that depend on space, and Cn, Cm, and M do not depend on x. Okay, so basically the integration just goes over the eigenfunctions. The integration is only over phi n and phi m. That's the integrand. What is the outcome of the integral? Well, that's the same outcome as, basically, it's the same every time. That is simply an overlap integral of phi n and phi m, which is going to be 0 unless n equals m. So that's this Kronecker delta one more time. And that means that I can say something about this double sum. This double sum becomes a single sum because unless n is equal to m, all other terms are going to be 0. The only summation that remains is the one where m equals to n. Okay, so m is equal to n, only one sum survives, and I get basically this. I get the sum over Cn modulus squared. The Cn modulus squared is a probability. And on the previous slide, if you remember, we looked at the same integral, namely the integration of the modulus square of the wave function over entirety of space for normalized wave functions equals 1, which means that this sum is 1. Okay? So this is another way of stating the same thing. These Cn's, modulus square of Cn, is a chance or a probability of finding the system in a state that corresponds to phi n. And all those chances together must add up to 1. And that's what it means. That's what the 1 means. It's simply, you basically add up all the possible scenarios, all the possible chances that I'm getting, which are included in the sum. So here the conclusion is the sum of the probabilities, Cn squared, equals 1. That is the result of this evaluation. And we will be using this result later on. Okay, now I'm going to make it a little bit more explicit because all of this, like last time, is awfully abstract. And I can see some of you guys already start to dislike me for that particular reason. So in order for you to appreciate me a little bit more, I would have to give some explicit examples, which I'm going to do now. Okay? So I'm going to give you an example where my phi n, which previously we have said is just some sort of eigenfunction of an operator, I'm going to show one possible way in which this phi n can take its form. This is my assumed phi n. Phi n is a sine function. Okay? A sine function, you see that n is in its argument. Okay, so phi n, if n is 1, then n is 1 over there, which is in the argument of the sine function. There's a pi in there, and then there's an x of course is my variable, because phi n is a function of x. L will correspond to a length, as I will show in a few moments. And those are all the parameters. So I have L, which corresponds to length, that's the length of my space that I'm considering. X runs from 0 to L. Okay? And then I have an n. N can be any number, any integer number, starting from 1 to infinity, and pi is just 1. Okay, so if I am putting that form into this general expression on top, what does it look like? It looks like this. And I'm assuming here that this n runs over only two values, namely n equals 1 and n equals 2. Okay? So I'm saying basically, my wave function is a sum of two eigenfunctions. One eigenfunction is phi n, where n equals 1, and the other eigenfunction is phi n, where n equals 2. Okay? And each one has a Cn in front of it. So I get C1, which is kind of like the fractional contribution of phi1, and C2, the fractional contribution of the second function, phi2. All I'm saying is that this particular wave function has two contributions. One contribution from phi2, one from phi1, and together they make up the entire wave function. Okay? It's a little bit more explicit because I say now what is the shape of each of those phis. Okay. So And I'm also going to give these CNs explicit numbers, just to give you a sense that they are actually numbers. Okay, so I'm going to say the Cn is 0.866, and C2 is 0.5. Okay, so if I write out the entire wave function, so I'm putting everything together now, I say this wave function, which has two parts, two eigenfunctions contribute with their own weighing factor, and so the total is going to be some sort of pre-constant, 2 over L, that is just a constant, times weighing factor of 0.866 times phi1. Phi1 is this sine function where n equals 1. That is the sine function with the argument pi x over L. That's the first contribution. Second contribution is 0.5, that is C2, times phi2. But now in the argument I see a 2, because that's the end. Okay? So that is the shape of the wave function. That's the general form. C1 times P1 plus C2 times P2. These eigenfunctions, by the way, you will see again. Okay? They are the solutions of the problem of a particle in the box. They have exactly this form. You'll see them again. So, but for now, we'll just assume that this is the shape. This is the wave function shape. Why this one? It's an arbitrary choice. Could be anything. I could sum over even more eigenfunctions, not necessarily 2, but to keep things somewhat simple, I'm going to limit the sum to two terms. Okay, so this is then the explicit form of the wave function, just written in a different way, a little shorter way, so you can see the numerical values. Okay, so let's put some pictures here. What is the shape of this first eigenfunction? It's this. That's a sine wave that runs from 0 to L. Okay, and it starts at 0, and goes up, and it ends at L. Again 0. So that's the shape of phi1 within the space 0 to L. That's what it looks like. That's the wave function. Or not the wave function, that's the eigenfunction, phi1. What about phi2? Because the total wave function has two contributions, phi1 and phi2. What does phi2 look like? It looks like this. It's also a sine wave, but because there's a 2 in there now, it makes actually an extra swing. It goes up and down. Again, between 0 and L. In this space of 0 and L, that is what phi2 looks like. Now, if we believe Max Born, then if we are going to take the modulus squared of these eigenfunctions, then I should be getting something that informs me about the probability. Okay, so if I take the same function and I do the modulus square, which is basically just taking the square, because the sine wave, this sine wave, is a real function. It's not imaginary. It's a real function. Just taking the square of that shape, you get that shape, and that shape has now a meaning. It's a probability of finding the particle, let's say an electron, between 0 and L. So if the electron will be described by just phi1, then I could say there's a very high probability that the electron is going to be here, and a much lower probability it's going to be there. That's what it means. If the electron would only be described by phi2, then the probability of the electron within this space, 0 to L, will be this. That is basically the square of that shape above. And that means that the electron has a high probability of sitting here, somewhat lower here, also high here, lower on the edges, and actually 0 right there. So you won't find the electron here at this position, which is very different from this guy. In this guy, the electron is most likely found, not always, but most likely, if you do a measurement, you have a higher chance of finding it here and here, in the middle of the box. That's different from phi2, where it says you have a 0 chance of finding it exactly in the middle of the box. So phi1 and phi2 actually tell different stories. They have different character. They have different character about the probability of the electron. Then my total wave function is a little bit of each, right? It is basically the sum, fractional sum, or a weighted sum of these two characteristics. Okay, so here's the kind of probability distribution of the electron within that space 0 to L. I'm going to ask myself, what if I integrate this eigenfunction over 0 to L? What happens? Okay? So it basically means I take the modulus square of P1, integrate it from 0 to L, and I can tell you that the outcome must be 1, because the electron must be somewhere in the box. The entire space is from 0 to L. The electron must be in the box, which means this integral equals 1. I don't even have to calculate it explicitly by integrating the sine function. Forget about it. I can just look at it and say, aha, the outcome must be 1. So that's what I'm going to use. Same for the second possibility. If the electron will be fully described by phi2, then it must be in the box somewhere. That means that the integration of the modulus square of phi2 over the entirety of the box also equals 1. Okay, but now I'm going to make things a little bit more interesting. What happens if I ask myself, what is the chance of finding the electron in one half of the box? Okay, so basically what you have to do now, you have to integrate it from half L to L. I'm not going to explicitly calculate this, because I'm going to use my physical intuition. I'm going to say, well, look, that distribution is symmetric. So there's a 50% chance of finding it on the left or right. So the outcome must be half. Okay, so there's no actual math here. This is just using my understanding of the problem to determine the outcome of that integral. I can do the same thing for the second case. Okay, I can clearly see there's a 50% chance of finding the electron on the right. Okay, that means if I integrate the modulus square of phi2 also from 1/2 L to L, the outcome must be half. Why do I tell you this? Because I'm going to use this result to study the behavior of the total wave function. Okay, remember the total wave function has the character of each of these phis in it with a certain weighing contribution. The weighing factors are of course C1 and C2, and I know what they are. I have actual numbers for it. Okay? So I'm going to ask myself this question now. First, if I have the total wave function, and its wave function is normalized, if I integrate the total wave function over 0 to L, then the outcome of that integral must be 1, because the electron must be somewhere. But what I'm asking now is, what is the probability of finding the electron on the right side of the box if my electron is described by the full wave function given there? Is it also half, as we saw on the last slide, or is it something else? That's what I'm going to calculate now. So I'm going to calculate the modulus square of the total wave function, which has two contributions, integrated from 1/2 L to L. Okay? So I'm going to split the parts, explicitly calculate this. The first contribution is the contribution from psi1. What I'm going to do is, I'm going to take the modulus square of the expression above, okay? The whole thing. And what I'm getting is going to be 3 contributions, namely the square of phi1, the square of phi2, and then 2 times phi1, phi2, right? That is what you're going to get if you take the square of the whole thing. So I got 3 contributions. The first contribution is the square of phi1, then the square of phi2, and then 2 times phi1, phi2. You also see, of course, that those weighing factors are in front. I can take them out of the integral in each of the cases. That's what I've done. So, I have 3 contributions. one from phi1, one from phi2, and then one that depends on both. It's the overlap of both that contributes. Can I calculate these things? I tell you, you can. Why? Because the first two contributions we just calculated on the last slide. The outcome of these integrals, 1/2 L over 2L, of each of these eigenfunctions was half. That was the outcome of the integral. Okay, so I can calculate that. C1 squared, I can also calculate. That's half. Sorry, that's 0.866 squared times half is the outcome of the first integral. The outcome of the second integral is also half. I'm going to multiply that by 0.5 squared, which is C2 squared. Okay? And so the last term is the most complicated term, because that depends on phi1 and phi2, both, and then integrated. So that is going to be the pesky one. Okay, I'm going to just tell you what the outcome is. You can do it. It's a product of two signs. You integrate it. We won't go into the nitty-gritty. But the outcome of that is going to be that term right there. So the primitive of the integrand is going to be that sine to the third. And I'm going to fill in the values L and half L. In front of it is simply the multiplication of those two coefficients, C1 and C2. Okay? So this allows me to actually calculate the chance, the probability of finding the electron on the right-hand side of the box if it is described by this full function psi. The outcome is this. Right? You just write it down. Here it is. Okay? 1/2 times the contributions from these coefficients, and then the last term, the last contribution, that integral is actually negative 0.386. Sorry, 368. And if you then add up all these contributions, you get 0.132. That is the chance. The chance of finding the electron on the right-hand side of the box is not 50%, it's actually 13.2. That's a little weird. How can that be? Okay? Well, it can be if you actually draw the shape of this total wave function. You see that the full shape of this guy has a little bit of character from phi1 and a little bit of character of phi2, right? On this side, the left side of the box, they both add up, but on this side of the box, the second function had actually a negative value here, while the first function was still positive. So it basically leads to this kind of little wiggle that dipped just below 0. So that's the shape of the full wave function, which is the contribution of both eigenfunctions included. And if you take the modulus square of this guy, you get the probability density distribution. Looks like this. You see, there's a much higher chance of finding the electron on this side than on that side. Right? So if I ask myself, what is the chance of finding it in this right-hand side of the box, I can see just visually that there's a much lower chance of finding it here than finding it there. Okay, so what is the bottom line here? There's a couple of messages in here. The first one is, if my electron is described by just a single eigenfunction, I get very nice results. Okay? I get very nice simple functions, relatively simple. And I can also see directly, like, what is the probability distribution of the electron? I get a pretty good physical sense. But the electron doesn't always have to be described by just a single eigenfunction. It could be a sum of several, like we have done here for 2. And then you see, you get very different shapes, and you get different behavior, different probabilities. Okay? So we want to discriminate those cases. We want to be able to tell ourselves whether or not the wave function that describes my electron is basically just one eigenfunction of my favorite operator. And typically the favorite operator will be the energy operator, as you will see as we move on. But sometimes the electron is described by several functions of that operator. like it is the case over here. Okay, so those two scenarios, we should be able to discriminate as we move along. All right, folks, I'll stop right there. See you back on Friday for another wonderful experience.